Hello everyone. So I thought I'd make this second video here to help explain a little more carefully like what it's expected for each question. So first of all, make sure you watch that first video where I review how to calculate torques, what rotational equilibrium means, and I walk through the lab. It is an older video, so some of the numbers of the questions are changed a little bit, but all the information is there. So how to calculate torques based on the meter stick, placing masses at different locations so that it balances, and then also the last set of questions where we use the simulation, the PHET simulation called Balancing Act. So all the information is on that first video. Make sure you watch it. That is important. But so this video, I'm just going to kind of highlight like what the questions are, because again, the numbers have changed. And I'll give you some hints on how to answer them. For the questions where you had to record data, if you go to my Word document handout, right, the first document, I filled in those already. So I give you the data to work with. Okay. All right. So let's go to question 1, which is in the lab manual. I think it's on the 3rd page. Yeah. So it says, does the center of mass of an object always have to be located within the matter of that object? And the example I give, the hint I give is, does the center of mass of a tire have to lie within the rubber material of the tire, or can it be in the center of the tire where there's just air, right? So that's what it's asking, right? So you want to make sure you answer that question. Does the center of mass of the object always have to be located within the matter of the object? All right, then the first thing that you have to do for the experiment is find the center of mass of your particular meter stick, and that is done for you. So I give you that position. Again, it's because we have these new meter sticks now, these new aluminum metal meter sticks. It's basically going to be right in the center of the meter stick, which is 0.50 meters. Okay, so that's filled in for you. This table on the Word document will be filled in for you, right? So make sure you include that in your lab report, 0.50. Okay, then the second part is verifying the second condition for equilibrium. And remember, the second condition for equilibrium, this is all covered in that first video, is the fact that the sum of the torques should equal 0. So what you're doing here is you're calculating the sum of the torques and seeing what you get. Okay? For the first question, this is question 2, we had, and you can kind of see it better here in this picture. So the center of mass is right at 50, right at the center of the meter stick. And then here, 20 centimeters to the left, or 0.2 meters to the left, I have a 200 gram mass hanging there. So 0.2 kilograms, right? It consists of these 2 hangers, and the masses to put on there is a total of 200 grams, so 0.2 kilograms. And I balance it with 100 grams on the right-hand side. So the meter stick is completely balanced. So if you were in lab, the first thing you would do is locate that position on the right-hand side where it balances. So we're going to say, and I gave you this data in the Word document handout, but we're going to say that it balances at 90.1 centimeters. So the first question wants you to figure out the moment arm for that 100 gram mass. Well, what does that mean? Remember, the moment arm is the perpendicular distance from the line of action of the force. The force acts vertically like this, right? Here, I'll draw it in here. The force acts vertically downward like that, right? So this is like the line of action. And the perpendicular distance from that line of action of the force to the axis of rotation, the axis of rotation is right at the center of mass of the meter stick at 50. That is what I'm looking for, right? That's what we're calling L2 in this case. So this is L2. So to find it, you literally take the 90.1 centimeters where it balanced, subtract the center of mass, which is 50. So you're going to get 40.1 centimeters, and then make sure you convert it to meters. right? Because we want everything in SI units. So it's 0.401 meters. So that's the value that you'll find already there for question 2. All right, question 3. Now here's where you have to verify the second condition for equilibrium. So you're literally going to calculate the sum of the torques and see what you get. And there's basically 4 torques. There's a torque due to weight 1. There's a torque due to weight 2. There's a torque due to the weight of the meter stick. And there's a torque due to the normal force that the clamp basically is pushing back up, right? You can think of it as like a knife edge where the axle rotation pushes back up. And we want to add those up and see what we get. But because, if you think about this, and again, I covered this carefully in the other video, because the force due to the weight of the meter stick and the force due to normal force pass right through the axle rotation, they have no moment arms. So these 2 torques are going to be 0. Okay? So the torque due to weight 1 is basically going to be weight 1, which, remember, the mass is 0.2 kilograms times 9.8. That would be the weight. The moment arm, the perpendicular distance, was 0.2 meters away. And that was a positive torque because, if I go back to the picture here, if you think about it, if this were the only force acting, right, pulling down, how would it rotate the meter stick? It would rotate it counterclockwise, right? Remember, counterclockwise is positive. Okay. Again, the reason why the torque due to the weight of the meter stick and normal force are 0 is because those are both acting right here, right through the axis rotation. Okay. And the reason why this one has a moment arm of 0.2 is this is the perpendicular distance. That would be 0.2 meters because we set it to be 20 centimeters away, right? 0.2 meters. Okay. So now I want to also find the torque due to weight 2 over here. Well, the weight was 0.1 times 9.8, right? The mass times G. So let me go back up. So this was oops, I'll do it in black again. So this was 0.1 times 9.8 times the moment arm, which is what you guys just found, right? Or what I gave to you guys. We assume it's 0.401. And that torque is negative, right? Because it would cause a clockwise rotation. And you want to do that calculation and see what you get. Okay? All right. Question 4. The next page. Assuming there was no error in placing the masses, reading the locations on the meter stick, etc., what should the answer to question 3 be? So what should, if everything is in rotational equilibrium, what should the sum of the torques equal? That's what it's asking, right? So just can just one simple answer number for that for question 4. Okay, and then for question 5, you would have performed the experiment again in lab, where now you put a 50-gram mass at 30 centimeters to the left of the center of mass, right, of the knife edge, the rotation point, and 100 grams at some distance to the right. Again, it's asking for the moment arm of that 100-gram mass when it completely balances. I give you that value. I think I made it 0.15. That data is in the Word document handout. So I want you to verify the sum of the torques again. So you're going to calculate, this is question 6, calculate the sum of torques just like we did for question 3. See what you get. Hopefully it's close to 0, right? And in question 7, what should the sum of the torques be? If everything were perfect, basically we know it should be 0, right? Okay, the next part was predicting the mass of the meter stick. So now we're going to use the fact that the sum of the torques has to equal 0 to predict the mass of the meter stick. So in this case, here's the setup. So the rotation point is moved 20 centimeters to the left of the center of mass. Remember, we're assuming our center of mass is right at 50 centimeters, right? 0.5 meters or 50 centimeters. So the rotation point, the axis rotation, is 20 centimeters to the left of the center of mass. So now, if you think about it, this is creating a force, right? I'm balancing everything by putting a 200-gram mass on the left-hand side. And also the weight of the meter stick is creating a torque, right? So this is creating, I have a force here, which is creating a counterclockwise torque. And I have a force here, which is creating a clockwise torque. So the first thing I wanted you to do was to figure out where to place that 200 grams so that everything is balanced. The meter stick is in rotational equilibrium. And again, I give you that data in the Word document handout, right? So I give you that value. I think I gave you as 0.152, I believe. So basically it was like 15.2 centimeters away from the axis of rotation. That's going to be the moment arm. Okay, so I drew it closer here, but it was actually further. It was like, I think this is at the location of 14.8, which means it would be 15.2 away, but then in meters, it'd be 0.152 meters away from the rotation point. Okay, once you have that, then you're going to calculate the mass of the meter stick. Again, how do we do this? We're going to use this fact that the sum of the torque should equal 0, right? So here, I'll actually do this on the side here. Again, in my first video, I walked through this, but let me just re-emphasize this. So now we're using the fact that the sum of torque should equal 0. I have a sum of the torque due to, I'll call it weight 1, that's the 200-gram mass. I have a torque due to the weight of the meter stick. There's also a torque due to the normal force. And those all have to sum to 0. But because the normal force acts right through the axis of rotation, there's no moment arm, so there's no torque contributed by the normal force, right? That's going to be 0, right? It's not going to cause it to rotate about that point, which is at 30 now. Okay, what does the torque do to weight 1? Well, that's going to be the force, which is the mass times 9.8, times the moment arm, which is the L that I gave you here, right? This value right here. And that torque is positive because if that were the only force acting, it would rotate the meter stick counterclockwise. And then I have one other force here, right? I have the force acting at the center of mass, and this is the weight of the meter stick, which is mg. So this is going to be the mass of the meter stick, which we're assuming we don't know, we're trying to predict this, times 9.8, that's the weight. What is the moment arm? Well, we set this up so that this perpendicular distance is exactly 0.2 meters, right? 20 centimeters, which is 0.2 meters. So the moment arm is 0.2 meters. And since this would cause a clockwise rotation, it's going to be a negative torque. So it'll be negative. And then it's got to equal 0. Okay, so once you plug in for your L here, you can solve for M. All right, and then you're going to compare. So question 9 is you're going to compare that value. That value that you just found is going to be your predicted mass of the meter stick. So that'll be this value right here that you predicted. And then I gave you, again, if you look in the Word document, I gave you that value for the experimental mass from the scale. They should be very, very close, and your error should be, close to 0, if not 0. Like definitely less than 1% for this. Okay, next, I have you answer question 10, which I think, I have a picture on the next page right here, where I set up a meter stick. Okay, this is one of the older meter sticks, like the white meter stick, and I have a tension pulling up at 10. So like think of it as like a string attached to it at 10 centimeters. So this is 0, 10, it's at 10. And there's a spring scale attached so I can read what the tension is there. I can read that spring scale. So you can think of tension A. Then I have another spring scale at 90 centimeters. So that's a tension B. There's a 300-gram mass. So that's going to create a weight, right, acting at 30 centimeters. There's a 200-gram mass acting at 70. And then you have the weight of the meter stick. Remember, the meter stick itself has a mass, and we're going to assume it acts right at 50. And the goal here is to theoretically compute the tension in A and the tension in B, and then compare. So these will be the theoretical values here that you're going to compute. And you're going to compare those to the two experimental values. How did I get those? I actually read these spring scales, okay? And I gave you those experimental values since you can't do this lab because of the snow. I gave you those two experimental values in the handout, right? The Word document handout, the first handout. So once you calculate the theoretical values, you can compare these by computing the usual percent experimental error. All right, let me help you get started on this, like how to calculate this, or question 10. Actually, let me go back because I think there was more room on the other page. Yeah. So I'm going to draw this out. So I have my meter stick. And then I have a tension TA. These are really vectors, right? Pulling up at 10. I have a tension TB pulling up at 90. And then at 50, I have the weight of the meter stick. I'll just call it W, which is mg. And then at 30, I have this, I'll call it weight 1, which is m1g. And remember, m1 was 300 grams, but we really want kilograms, so I'll just write it as 0.3 kilograms. And then at 70, I have weight 2, which is m2g, where m2 is 200 grams, but that's the same as 0.2 kilograms. Okay, and I want to figure out what TA and TB are, right? What are those tensions? What are those forces, right? The tensions are just forces. Okay, so to do this, I could use the fact, since I know that this meter stick is in rotational equilibrium, right? It's static, it's not rotating at all. That means the sum of the torques about any point I choose must be 0, right? That's what the second condition for equilibrium means. So the sum of the torques must be 0. The question is, where do I put my axis of rotation? Well, I don't know TA, I don't know TB. I would like to eliminate one of them right off the bat, at least for now. Let's say I want to solve for TA, so I don't want TB to appear in my torque equation. So a good place to put the axis of rotation then would be right at TB, right at 90 centimeters here. That's going to be my axis of rotation. Okay, why is that? Because now there's no moment arm due to TB about that point, so it will not contribute a torque. Okay, so now when I do my sum of the torques, again I'll go black. Sum of the torques must equal 0. I have a torque due to TA. I have a torque due to weight 1. I have a torque due to the weight of the meter stick. I have a torque due to weight 2. I have a torque due to TB. That's got to equal 0. But this one is 0. Why? Because the moment arm is 0, right? Remember, in general, a torque is always going to be plus or minus, depending on whether it rotates the object clockwise or counterclockwise, force times moment arm. Okay, so what is the torque due to TA? Well, it's going to be TA, right? That's the unknown. That's the unknown force. And then the line of action of TA is just vertical like this. So what's the perpendicular distance from the line of action of that force to the axis of rotation? It must be this horizontal distance, right? That's the one that's perpendicular. So we don't need any trig yet, right? The next problem I give you, you're going to need trig, but for now we don't even need trig. These are nice horizontal distances, right, to figure out our moment arms. So what is that distance? Well, 90 minus 10 is 80 centimeters, but I want meters, so it's going to be 0.8 meters. And then the only other question is it positive or negative? Well, if TA were the only force acting, how would it rotate the meter stick about this axis of rotation at 90? It would rotate it clockwise, right? And by definition, that's a negative torque. Then the torque due to weight 1 is going to be the weight, which is 0.3 times 9.8. So here I had to multiply. You have to be a little careful, right? The tension was already a force, right? That's my unknown. I didn't have to multiply by 9.8. But here I want the force, which is the weight, and I was given the mass, so I have to multiply by 9.8 to get the force. Now I need to multiply that force by the moment arm. Well, what's the moment arm for that? Well, what's the distance from the line of action of this force to the axis rotation? This perpendicular distance is just 90 minus 30, which is 60, right? So 0.6 meters. And since that would rotate the meter stick counterclockwise, that's going to be a positive torque. Then you keep going. I think I gave you the mass of the meter stick. It's given on the Word document handout. I think I gave it to you as 0.1936 kilograms, right? 193.6 grams or 0.1936 kilograms. So basically, the torque due to that weight is going to be, first of all, I need to calculate the weight. So I need to multiply that 0.1936 by 9.8 times the moment arm, which is going to be 0.4, right? That torque's also positive. Then I have a 200 gram mass for the last one for weight 2. So I have 0.2 times 9.8 times the moment arm. This also happens to be 0.2, right? The distance away is 0.2, that perpendicular distance. And that one's also positive, and that equals 0. And notice here, you can solve for TA. Okay? And then once you have TA, how do you find TB? Well, one way of doing this is you could go back and move the axis of rotation to be at the 10 here, and then figure out all the moment arms, or all going to kind of reverse here. But an easier method is, since we know that the meter stick is also in translational equilibrium, right? It's in rotational equilibrium. It's also in translational equilibrium, which means the sum of the forces is also 0. So you could just say, well, since it's in translational equilibrium, I know that the sum of the forces, in particular in the y direction, since all our forces are in the y direction, is 0. So that means that TA, which is positive, right, plus TB, which is positive, minus weight 1 minus the weight of the meter stick minus weight 2, that's got to equal 0. Right? And remember, these weights are just the mass times G. And we know TA, right? We just calculated TA here from above using torques. So the only unknown is TB, and you can solve this for TB now. Okay? And then once you have those values, then you can compare what I gave you for the experimental values. Here's what I actually read in the spring scale. These are the ones that you just calculated using torques and the fact that the sum of the forces equals 0 as well. Right? So then you'll be able to compute the percent experimental error. Okay, the other one I want to walk through carefully is, so we're going to skip this question 11. We're going to go right to 12. So here's the, let me go to the next page. Here's the picture for 12. So basically I have this wooden beam. There's a weight of the beam acting at the center of mass, right, which is 30 centimeters away from the axis of rotation, or 0.3 meters away. I have a hanger hanging from the end, which is 300 grams, so it has a weight, right? You can calculate it. 0.3 times 9.8 would be the weight, and it has a moment arm, which is this distance, which is 60 centimeters, right, or 0.6 meters. There's also a joint force at the joint, but that's not going to affect anything. It's not going to appear in our equations because it doesn't contribute a moment arm. It doesn't contribute a torque about this point, right? Because there's no moment arm. There's like 0 moment arm here. And then there's a string, right, with a spring scale again, where the string attaches 40 centimeters from the rotation, and then it attaches up here at 46 centimeters. Okay, up to the rod stand here. The whole idea here is to calculate theoretically what that tension in the spring scale is. Okay, I give you all the data for the mass of the beam, the mass of the hanger, all these lengths here, right? So that's all given in the problem. The way to think about this, though, let me go back a page for a second. So you want to figure out what the theoretical value is. This is the value. This is what you're trying to find. This is the tension in the cable, like the string. All right, that's what you're trying to calculate. So again, if you look at my Word document, I give you the experimental value. So I just read the value from the spring scale. I think it was like 8.30, something like that. Your goal is to calculate the theoretical value and then compare them by calculating the percent experimental error. All right, so I'm going to give you some hints. What I would do first is find the moment arm for the tension. So the other ones are easy, right? For the weight of the beam, this is the line of action, right? It's acting along this line. So what's the perpendicular distance from the line of action of that force to the axial rotation? That's just this distance, right? That is the perpendicular distance. So the moment arm for the weight of the beam is just 0.3 meters. For the hanger, same thing, right? This is the line of action. The moment arm is the perpendicular distance from the line of action of the force to the axial rotation. It's just this distance. So that'll just be 0.6 meters. The problem is the spring, right? This is the line of action of the tension in the spring. So something like this. And we want the moment arm, which is the perpendicular distance from the line of action to the axial rotation. So in this case, we want this distance, which is perpendicular. So you need to find, I'll call it L for the tension, LT, L for the tension. You need to find that particular distance, right? In order to apply the sum of the torques. So what I would suggest doing is first I would find this angle. And you can find the angle by thinking of this right triangle, this large right triangle. Again, we know this length, right, is 0.46 meters or 46 centimeters. And we know this length is 0.40 meters, right, or 40 centimeters. So how do I find the angle? You just use trig, right? Think of opposite over adjacent, and that'll give you the angle. It'll be the inverse trig function when you do this. Okay, once you have that angle, how do we find what we really want? Remember, we really want this distance right here, the one that's perpendicular. So if we draw that new triangle, I'm looking for this. This is like my L for the tension. I know this length, and now I'm going to know this angle, so that will allow me to calculate that moment arm. Okay, and then once you have all the moment arms, you can just use the fact that the sum of the torques has to equal 0. So now we have a torque due to the tension plus a torque due to the weight of the beam plus a torque due to the weight of the hanger plus a torque due to the joint force equals 0. And this one, the one due to the joint force, is 0. Why? Because there's no moment arm, right? It goes right through the axial rotation. We're considering the axial rotation to be right here where the bolt is. All right, so I'll let you guys think about that, but the whole goal is to calculate T. So you want to find the tension in the string, T. All right, and it should be pretty close to the value that I gave you experimentally. Right, it should be pretty close to this value that I gave you experimentally. So you'll know whether you calculated correctly or not, because it should be very close to that. You should have a very small percent experimental error. Okay, and then the last part of the slab was basically by the way, here's the actual setup, right? So here's the spring scale that I read. I think it was like 8.30 is the value I gave you. The last part, I explained this pretty carefully in the last video. So I want you to watch that last video. I think it's really important to see. It gives you all the background information. And what you're doing for this part is for question 14, you're setting this up where you have 15 kilograms at 1 meter to the left of the axis of rotation, 20 kilograms at 0.5, and then you're calculating, so using the fact that the sum of the torques is equal to 0, you're calculating where a 20 kilogram mass will go, like where it'll be placed, so that when you release this, it's completely balanced, okay? So I need you to show me that calculation. You're going to basically get some value here of where it's placed. You're basically going to get the moment arm, right? The moment arm is going to be the answer here. Okay, and to check it with the simulation, and it should balance exactly with whatever you calculated here for the moment arm. But you want to make sure you show me that calculation. Then the next part is you're putting, do I have a picture of it? Yeah. Now you're putting 5 grams at 1 meter to the left, 20 grams at 0.5 meters to the left, and you're balancing it with this unknown mass of package A at 0.75 meters to the right. So now you're told, if you look at this, it's completely balanced, right? So everything's in rotational equilibrium. So using that fact, I want you to calculate what the mass of package A is. So again, you're just going to do sum of the torques equals 0, and you're going to find the mass of package A. Okay? And then finally, there were several other like mystery objects. So package B, C, and D. This is just trial and error. I want you to find what those other masses are just by playing around with the simulation. And again, I think the easiest way to do that is to place a known mass at, say, 1 meter to the left, and then the unknown at 1 meter to the right. And if it balances, it must be the same mass, right? Because the torques would balance. If it doesn't balance, then it can't be the same mass. So however you want to figure it out, you don't have to show me any calculations for question 16, but just list the correct masses for the other packages for B, C, and D. Okay, so hopefully that was helpful. Definitely watch the first video as well, though, because it gives you all the background information. And then this kind of, this one went in detail with exactly like what questions you need to answer, and I give you a bunch of hints. Great, thanks.